Hello everyone. In this video, we are going to talk about gradients of the loss function in logistic regression. This is the agenda of today's video. First, I will give a brief review of logistic regression, and then we will attempt to solve the analytical solution for logistic regression. I use the word attempt because, as you will see later, that we really couldn't solve the analytical solution because of the nonlinear nature of logistic regression, but that is completely fine because while we are attempting the analytical solution, we are going to solve the gradients of loss functions of logistic regression, which will be useful in the next video when we talk about gradient descent. And lastly, I'm going to express the gradients of the loss function in vector and matrix notation. Okay, so let's get started. A quick review on logistic regression. The backbone of logistic regression is really the sigmoid function, which looks like this. And if we treat sigmoid function as a function of z will goes from minus infinity to plus infinity, and then the sigmoid function output will goes from 0 to 1. And this z in the logistic regression is nothing but a linear combination of our input features. So x subscript 1 is feature number 1, x subscript 2 is input feature number 2, etc. And then beta is the intercept. So when we talk about logistic regression, we are really thinking about sigmoid function as a function of the linear combination of the input features. And because the output of sigmoid function ranges from 0 to 1, therefore we can treat it as a probability. And in logistic regression, the probability of class 1 is simply the output of sigmoid function, and the probability of class 2 is 1 minus the sigmoid function. Okay, and then as I mentioned in my previous video, logistic regression is basically a binary classification problem where we are trying to classify a sample, whether that sample belongs to class 1 or class 2. And with this probability output, we can assign the sample to class 1 if the probability of class 1 is greater than 0.5. Other than that, it will be assigned to class number 2. So that's how logistic regression works as a binary classification problem. Also, in my previous video, I have derived the loss function of logistic regressions, and basically the primary goal for logistic regression is to find this w, which are the weights, and beta, which is the intercept, that will minimize this loss function of logistic regression. Okay, let's talk about some notation here. This n is the number of samples, and then this m is the number of features. I'm going to use the subscript for the feature number, and then for the sample number, I'm going to incorporate a number inside this open and close square bracket. So for example, in my previous video, I gave this example where we want to classify an employee is a manager or not. We are going to have two features in this particular example, so this will be x number 1 and x number 2. X number 1 is the salary of the employee, and then x number 2 is meetings per day. Each row represents 1 employee, so right here we have 5 employees, which means that this $130,000, that's from feature number 1 and then employee number 1. Okay, this meetings per day 2, that's feature number 2 from employee number 3. Okay, this y is basically just the true output. So if the employee is manager, it is equal to 1, and if employee is just a regular employee, then it is equal to 0. Before we move any further, let's first simplify the loss function. So this first expression here is simply the loss function that I copied from the previous slide. And I really don't like this beta. I want this beta to be also a form of x times w. So we can do that by creating a new input feature x with subscript n plus 1 equals to 1 for all I, and set beta equals to w n plus 1. So if we do that, then this above expression can be written as this below expression, where now every term inside the sigmoid function is equals to x times w. That will simplify the derivation later. So if we do that, our task now is to find the optimum w1 all the way to wn plus 1. Let's now copy the expression of the loss function to the top of this slide. Naturally, if we want to find the w's that minimize the loss function, what we need to do is to take the derivative of the loss function with respect to each w's and then set the derivatives equals to 0. That way we will get a system of equations, and the optimum w's can be solved by solving the system of equation. Because of the symmetry nature of all the w's, we can first only focusing on the derivative of loss function with 1 wj, and then after we are solving for these expressions, all the w's will have the same expression. Okay, if we do that, you'll see that yi is equals to a constant with respect to wj, so nothing is going to change. And we are going to take the derivative of this log of sigmoid function with respect to wj. In the second term, 1 minus yi is again a constant with respect to wj, so nothing is going to change. And we are going to take the derivative of the log of 1 minus the sigmoid function with respect to wj. Set that equals to 0. This expression is quite long, so let's break it into piece by piece. Let's now focus only on this term here, which I'm copying it into the next line. Next, I'm going to replace this linear combination of the input features into just zi. Remember, this zi can be representing the linear combination of the input features. And if we write that, now we can use the chain rule to break this derivative into two terms. The first term is the derivative of the log of sigmoid of z with respect to z. Multiply the second term, which is the partial zi over partial wj. Now this partial zi over partial wj is simply equals to xji. This is because this z is simply a linear combination of x times w. So partial z partial wj will remove all the terms except the terms of xj times wj. And then the derivative of xj times wj is simply the xj. Now we need to solve for this partial derivative of log of sigmoid of z with respect to partial z. That is equals to 1 minus sigmoid of z. How did I derive that? Let's look at the next line. I am copying the expression of partial sigmoid of z, partial z into the next line. The derivative of the log function is simply the derivative of the function by itself divided by the function. So now we need to solve for this term over here, the partial derivative of sigmoid functions with respect to the partial z. To do that, let's first review the expression of sigmoid function, which is equals to 1 over 1 plus exponential of z. This is another way of writing it, which is equals to 1 plus exponential of minus z raised to minus 1. So if we want to take the derivative of sigmoid function with respect to z, we can first bring this exponent into the front. So minus 1 will be here, and then minus this minus 1, therefore there will be minus 2. Using the chain rule, we need to multiply the derivative of what's inside the parentheses, which is equals to exponential of minus z. But because we need to do another chain rule again, the derivative of minus z is minus 1. So we are going to have a minus sign here. After some manipulation, you'll see that partial sigmoid function partial z is equals to this expression here. Okay, we can move that to here. 1 over sigmoid function is simply 1 plus exponential of minus z. This term and this term on the denominator can cross out each other, so we are left with this term over here. And if we do some manipulation, we can see that this term is actually equals to 1 minus the sigmoid function of z. So we can replace this term with this expression here. On this new slide, I already replaced the first partial derivative with the term 1 minus sigmoid functions times xj. We now need to focus on this second partial derivative. So let's first copy the expression to the next line and replace the linear combination of input features with z and split this partial derivative into two terms with the chain rule. So first term will be the partial log of 1 minus the sigmoid function partial z. The second term will be partial z over partial wj. And again, partial z over partial wj is simply equals to xj over here. So we are left with solving this partial derivative term, and that will equals to minus the sigmoid of z. So how do I make that conclusion? We need to look at the next line. So let's copy the expression to the next line. The derivative of the log function is the derivative of the function by itself divided by the function. And this first partial derivative is equals to minus the partial sigmoid function divided by partial z. Partial sigmoid function divided by partial z, we already solved that in the previous slide, which is equals to this expression here. So we can replace that over here. Remember, there's a minus term. And then 1 over 1 minus the sigmoid function. Okay, 1 minus the sigmoid function is 1 minus this term over here. After some manipulation, you will see that 1 minus sigmoid function is equals to this term over here. So 1 over this expression, we are going to simply invert the fraction and then put that into the second term over here. Now you can see that this term and this term will cross out. And then this term will cross out one of that term. So 1 over 1 plus exponential minus z is simply the sigmoid function, and remember we have a minus term here, so that's equals to minus the sigmoid functions, and we can put that expression over here. With that, we conclude that this second partial derivative is equals to this term minus sigmoid functions times xj. We can now replace the second derivative with this term sigmoid function times xj. And then we are going to put the minus sign here, replace the previous plus sign. We can further simplify this expression. So as you can see, this first term and this second term, they both has xj. So what we can do is pull the xj out, and we are left with y times 1 minus the sigmoid function minus 1 minus y times the sigmoid function. We can multiply this expression out, so it becomes y minus y times sigmoid functions minus sigmoid function plus y times sigmoid functions. Okay, this term and this term will cancel out each other, so we are left with this expression. Okay, and then of course the z is equals to the linear combination of input. Set that equals to 0. Finally, we derive the expression of the derivative of loss function with respect to wj, which is equals to that. And we are interested in the derivative of loss function with respect to all w's. So we can write each one of them into a column factor. And then the expression for each one of them is simply this expression, but replacing this xj with appropriate number. So the first expression will be x with subscript 1. The second expression will be x with subscript 2, etc. Each of the expression equals to zeros. Now we have this system of equations. We have total n plus 1 equation, and we have total n plus 1 variables, which are w1 all the way to wn plus 1. So we should be able to solve this system of equation, but because this nonlinear nature of the sigmoid function is very hard, or it's probably impossible to find the analytical solution, we can always use the numerical methods to solve the equation, and then once we do that, the W1 to Wn plus 1 that we are going to get is the optimum parameters for the logistic regression. This vector of the loss function with respect to all the w's is called the gradients. And even though we are not able to solve the system of the equation analytically, the derivation of this gradient is still useful in the next video when we are going to talk about how to solve the logistic regression with gradient descent. This expression of the gradients can be further simplified into a vector and matrix notation. So that's what we are going to do next. When we talk about vector and matrix notation, the convention is to use Boolean symbol, and capitalized Boolean symbol will be representing a matrix. Lowercase Boolean symbol will represent a column vector. So we can represent our inputs as a matrix X, where each column representing a feature. So column number 1 is feature number 1, column number 2 is feature number 2, and then each row represents a sample. So row number 1 is sample number 1, and row number 2 is sample number 2. We can also rewrite this matrix capitalized X into this form, where each of these italic X representing a feature column vector. Okay, so X number 1 is a column vector, X number 2 is also a column vector, all the way to Xm plus 1. Regular X without italic representing a sample. So X1 without this italic is a column vector of sample number 1. But in this X, sample is representing as a row vector, so we need this transpose symbol. So this is a second way to represent our matrix X. First way is to use the feature. Second way is to use the samples. We can represent all the output Y as a column vector, and then represent the entire column vector as a Boolean symbol with lowercase y. And then this is the gradient, also representing a vector of the derivative of loss function with respect to all the w's. All the w's can be representing as a column vector as well, with a lowercase symbol w, and the sigmoid function of z can also be represented as a column vector. This z1, z2, and zn, because it is a linear combination of the input and the w's, we can represent z1 as x1 transpose times w, z2 as x2 transpose times w. Another way of representing this vector is to first calculate all the x1 transpose, x2 transpose with w, and then do a sigmoid function on each of the term. And this term inside the parentheses is equivalent to the big X times the w. Now let's look at how we can rewrite the gradient of loss function with respect to wj into a vector matrix notation. So this is the expression that we derived earlier. Now pay attention to this summation. If we expand that out, it simply equals to xj1 times y1 minus the sigmoid function of z1 plus xj2 times y2 minus sigmoid function of z2 all the way to xjn times yn minus sigmoid function of zn. We can represent this summation as a vector multiplication. So it's going to equals to this row vector times a column vector. This row vector is simply xj transpose, and then this column vector is simply the column of y minus the column of sigmoid function. Next, we need to expand this gradient of loss function with respect to a single wj to the entire gradient with respect to all wj. So to do that, we need to first review this expression that we derived previously. The term on the left of the equation is simply the gradient, and then the term on the right of the equation is the gradient expression. We can replace each of these terms with the vector notation that we just derived from the previous slide. And because each term has this minus 1 over n in front, so we can pull that out. And then the rest of the expression can be split into a matrix multiplication. Okay, the first term is a matrix with each row representing a feature, and then the second term is actually a column vector y minus sigmoid function. Now this term is actually equals to the big X transpose, so we are going to replace with big X transpose. The sigmoid function is equals to the sigmoid function of x times w, as we derived before. So in the end, we are left with this expression. The gradient of the loss function is equal to 1 over n times the big X transpose multiplied by y minus sigmoid function of x times w. This expression will be very useful in the next video when we are going to talk about how to solve logistic regression using gradient descent. And this is pretty much it for this video. I hope you enjoy. Thank you for watching. If you like this video, don't forget to like and subscribe. Other than that, I will see you in my next video. Thank you.